Imagine you need to find every record of a shark in a massive list of ocean animals. Your natural instinct is to start at the top, pull out the first file, and check the contents. Early databases like IMS and Codicil mimicked this behavior. Developers interacted with data through imperative programming, a style defined by providing the computer with a specific list of instructions. As this flowchart shows, the developer has to step through the data. You check the condition, save the match, and move to the next item. In the industry, we call this manually writing the access path. Defining the access path gives a developer total control over the process, but it also locks the machine into a rigid, sequential sequence of operations. That sequential logic works for a few hundred items, but modern data realities are different. We are now asking systems to process billions of rows of data simultaneously. Hardware has adapted to this scale by adding more processor cores, rather than just increasing the raw clock speed of a single chip. This creates a physical bottleneck. Because an imperative loop requires a specific order, work cannot be divided. 3 of 4 CPU cores sit idle. Forcing that sequential logic across parallel processors causes synchronization delays and logic errors, effectively crashing the system's efficiency. By micromanaging exactly how the computer executes the search, human developers created a hard physical limit on how well their applications can scale. The solution arrived with the relational model and SQL, which abandoned the step-by-step instruction manual for something more abstract. This is the declarative approach. Instead of providing instructions on how to find the data, you describe the pattern of the data you want. The computer handles the rest. Your query doesn't go straight to the data. It enters the Query Optimizer, a hidden engine exploring dozens of execution paths. Acting as an automated traffic controller, it checks indexes and autonomously chooses the fastest route across every available CPU core. The developer no longer needs to worry about the access path or manual threading. Decoupling your intent from the machine's execution allows the database to adapt to new hardware without you rewriting a single line of code. We see this same tension between specific instructions and final intent when we move from the database to the web browser. Manipulating web page styles imperatively with JavaScript is notoriously fragile, but CSS is declarative. You describe the end state, allowing the browser engine to optimize the rendering process in the background. Even so, the industry briefly relapsed. Early big data tools like MapReduce forced engineers back into writing imperative functions to process data across clusters of machines. That regression proved so tedious that developers quickly built new declarative layers, like MongoDB's aggregation pipeline, to hide the imperative mechanics once again. This visualization shows a graph data model. These structures are designed to manage sprawling, unpredictable webs of many-to-many relationships. Querying this geometry in traditional SQL is difficult. Tracing a path through multiple relationships requires dozens of lines of dense, recursive code that is hard to read and even harder to optimize. Graph-specific languages like Cypher solve this by using pattern matching. This 29-line block of recursive SQL logic can be expressed in just 4 lines of declarative Cypher. The declarative philosophy remains the same, but the syntax evolves to match the specific shape of the underlying data. The choice between imperative and declarative isn't a stylistic preference. It is the demarcation line between human intent and machine execution. The ultimate benefit is abstraction. If a database engine is updated tomorrow to run 10 times faster, your declarative queries will automatically inherit that speed without human intervention. Imperative code, by contrast, becomes a legacy burden the moment the underlying hardware or storage mechanics change. In an era of massive data and parallel computing, micromanagement is a liability. The most scalable action a developer can take is to clearly define the destination,